and we want to start talking about free fall and weightlessness. They're actually one and the same thing. And what I'll do here is that I'll try to demonstrate that. And if we were in person and we could actually do this, I would have a demo for you. And this demo, what we do here is that we drop 2 different tennis balls. And the way I would drop them is that I would do the following thing. So I have one tennis ball. And what we know is that when I look on the inside of the tennis ball, this guy right here is air-filled. And that's a normal tennis ball. So therefore, this guy must have less mass. And then I have a second tennis ball. And when I look at what this tennis ball has inside, I went in, and I think I already said that, I drilled a hole into the tennis ball and I filled it with lead shot. So there's more stuff in this side. So this guy is a lead-filled tennis ball. So therefore, it has more mass. So what I would do now is that I would then drop them simultaneously. From the same height. So in other words, I would take this tennis ball and this lead-filled tennis ball. And then what I would do here is that I would drop them onto the ground. And the question here is that if they both start with the same initial speed of 0, and so the question that I'm asking now, which tennis ball hits the ground first? And the answer is that neither. They both hit the ground. The ground at the same time. Okay, they both hit the ground at the same time. So what you're seeing here is that when I look at this tennis ball versus this other tennis ball, right before they hit the ground, they have the same speed. Right? So when I look at these guys, both of these tennis balls have the same speed when they hit the ground, right before they hit the ground. They hit the ground with the same speed. The big question, though, is why? Why do they both hit the ground at the same time? Well, since we're talking about forces, the most common answer is as follows. Since we are talking about forces, the most common answer is they have the same force of gravity. And the answer is that's not correct. So when I look at this answer here, And it can't be that. And the reason why that is you have to remember weight is equal to the force of gravity. They're exactly the same thing. And this implies here is that both tennis balls do not weigh the same. So when I look at one of these, when I compare these tennis balls, when I look at this tennis ball versus this other tennis ball, the air-filled tennis ball has what? Less stuff inside. Whereas the lead shot tennis ball has more stuff inside. So when I look at this thing here, what I'm seeing here is that this guy has a small force of gravity, smaller weight, and this one has a larger force of gravity. So the force of gravity is not the same on both tennis balls. So then what we say here is that the force of gravity is not the same on each tennis ball. So to understand the question why, we have to talk about Newton's second law. Newton's second law is the one that explains what's going on. So let's go do that. So what we want to do here is that I'm going to change this just a slightly different way. And what we're going to do here is that we're going to use Newton's second law to explain why they hit the ground at the same time. So what we're going to do here is that suppose we drop blocks. Okay, so I'm going to drop blocks. So let's go drop a block. So I'm going to drop this block right here. And when I look at this block has a mass m. So one block has a mass m. So then when I look at this force of gravity, it's going to look that big because it's directly proportional to the mass. Now what I'm going to do here is that I'm going to have two blocks that I'm going to drop. So here's this block, and then there's this block. So when I look at the masses of these guys, because there's two of them, and this is about one square, then the combination of these two imply that it's got to be two squares instead. So that force of gravity should be twice as big. So now, what does N2L tell us here? N2L tells us that when we go to look at the force of gravity, right, let me be careful here. So I should say one thing just to remind you. So remember, weight is what? The force of gravity, but that's mass times acceleration. And in this case, the acceleration must be the acceleration due to gravity. So that's what weight is. So what I'm going to do here is that now let's go look at this thing. So picture-wise, what am I seeing here? What I see here is that one of these guys, the first block, so if I look at block one, a single block, what I see here is it has a force of gravity this big. And when I look at two blocks, its force of gravity has to be twice as big. Now, when I now look at Newton's second law, what does it say here? Well, this guy has what? It just has a little tiny mass. So this has this amount of mass, but the 2 block must have what? Twice the size of the mass. And so according to Newton's second law, it's this ratio that gives us what? The same acceleration. And to see this, we can look at this thing mathematically. So now if I look at the equation for Newton's second law here, I know that the first single block has mg as its force of gravity, whereas the 2 blocks, there's 2 masses, so the weight must be twice that of the first one. And so when we look at this guy here, we then see that this is 1 block, but the 2 blocks has 2 masses. So when I go and I look at this, you can see here is that the mass cancels out in the top and the bottom. These 2 masses cancel out with those masses. So what am I left with? I'm left with the acceleration due to gravity. So both blocks have the same acceleration. So what we can do here is that we could summarize this is that the blocks fall with the same acceleration because their force to mass ratio are the same. Okay, they are the same. Believe it or not, this result, I think, is quite shocking. This result is quite shocking. Because we rarely encounter free fall motion, which means what? No air resistance. We really don't encounter air resistance unless it's a very special situation. Because you already know that, let's say that I take a sheet of paper. Okay, so here's a sheet of paper. So imagine that I have a sheet of paper and I'm going to drop it. Okay, so this guy here is a sheet of paper. And then what I'm going to do here is that I'm going to take a big Mack truck. And so when I look at this Mack truck, right, I'm going to drop both of these guys at the same time. And what we're going to do here is that when we drop them at the same time, and I ask you, which one is going to hit the ground first, right? Which one hits the ground first. In free fall. Remember, no air resistance. The answer is they hit the ground at the same time. They both hit the ground simultaneously. And that is just shocking. It is really, really shocking. And the reason why it's shocking is that our experience is not with free fall at all. We always have air resistance. And so what we do here is that we then go to a video by Brian Cox, and he is a astrophysicist from England. And what they do in this video here is that they drop a bowling ball versus a feather. And this is what we want to go do. So let me go share my screen. Let me make sure I got everything set up. And here it is. So I'm not going to play the whole thing, but I'm going to speed through some of the portions. But we'll watch it right now. Here we go.
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. And it's kind of got an eccentric construction, which is part of its history. It was built in...
So now that you see that, I'm going to race forward, and here's where they're going to start here.
Present on the outside when it's pumped out to the conditions of outer space. Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So in order to see the true nature of gravity, we have to remove the air.
So then I'm going to move this forward now.
Near perfect vacuum inside.
6104 manual, 10% over. 10, 9, 8, 7, 6, 5, 4. Cameras on, 2, 1, release.
Look at that.
They came down exactly the same. Wow. Look.
That's pretty astounding. You gotta admit. So